Today I am going to start module 1 of chapter 6. The chapter 6 is devoted to the theory of hyperbolic differential equation. Amongst all hyperbolic equation, the wave equation occurs most frequently in many physical problems. Chapter 6 is divided into 5 modules. In module 1, we shall discuss about the occurrence of wave equation in many problems in physics. In module 2, we shall discuss about solution of one-dimensional wave equation. In module 3, we shall discuss about solution of two-dimensional wave equation, and in module 4, we shall discuss about the solution of three-dimensional wave equation. Lastly, in module 5, we shall discuss about general solution of a wave equation. Firstly, we shall discuss about occurrence of wave equation in many problems in physics in module 1. For that discussion, we need to go to the slideshow. So, we are going now to our first slide. As I have told that one of the most important hyperbolic equation is the wave equation. The wave equation is given by del 2 phi del t square equals to c square grad square phi, which is written in equation number 1, and this c represents the wave speed. Now, if we assume a solution of equation 1 in the form small phi equals to capital phi into e to the power I k c t, that means we are assuming a periodic solution in time of equation 1, then substituting this in equation 1, we get an equation which is written in equation number 2, grad square plus k square phi equals to 0, and this special equation is called Helmholtz equation or the space form of the wave equation. Suppose we want to solve a physical problem where we have to find the transverse displacement of a string, and the string is of uniform density rho and it is stretched to a uniform tension capital T. The string in the equilibrium position coincides with the x axis. Let the string be disturbed slightly from its equilibrium position, and y, which is function of x and t, denotes the transverse displacement from the equilibrium position. Then this transverse displacement y will satisfy the one-dimensional wave equation which is written in equation number 3. Del 2y del t square equals to c square del 2y del x square, where c square equals to capital T by rho, where capital T is the tension of the string and rho is the uniform density of the string. Suppose we want to solve this problem together with the condition which is given such that the string is fixed at some point x equals to a. Then we have the condition y at a t equals to 0 for all t. Then our physical problem becomes to solve the equation 3 together with the boundary condition y a t equals to 0. Now I shall discuss another problems in physics where we are interested to find the longitudinal vibration in a bar. So, for that we consider a uniform elastic bar of uniform cross section whose axis coincides with the x axis such that each point of a typical cross section of the bar takes the same displacement xi. Then xi will satisfy the one dimensional wave equation which is written in equation number 4. Here c square is given by E by rho, where E is the Young's modulus and rho is the density of the bar, and the stress sigma at any point of the bar is given by the Hooke's law. The Hooke's law says that stress is proportional to strain. So, which is written in this equation sigma equals to E into del xi del x, where del xi del x represent the strain and E is the proportionality constant which is known as Young's modulus. We also assume that the bar for 0 less than equals to x less than equals to a is held at rest initially, and the end, which is denoted by x equals to 0, is subjected to the prescribed velocity ut. That means the end x equals to 0 has the velocity ut and the other end x equals to a is rest. Then the longitudinal displacement, which is denoted by xi of section of the bar, is determined by the wave equation which is written in equation number 4, together with the initial condition xi equals to 0 and del xi del t is equals to 0 at t equals to 0 and for 0 less than equals to x less than equals to a. And we have the boundary conditions del xi del t equals to ut at x equals to 0 and del xi del t equals to 0 at x equals to a. Thus, we need to solve wave equation 4 together with the initial conditions which are written here and the boundary conditions which are given in the last line. Now, we are going to discuss how wave equation can come in some electrical problem. For this problem, we consider the flow of electricity in a long insulated cable, show that the current is I and voltage is denoted by capital E with one spatial coordinate small x and time by t. Then the fall of potential in a linear element delta x, which is situated at a point small x, is given by the equation minus del E equals to I r del x plus L del I del t into del x, where R is the resistance per unit length and capital L is the inductance per unit length. Now, if we divide this relation by delta x and take the limit as delta x tends to 0, we get the differential equation del E del x plus I r plus L del I del t equals to 0, which is written in equation number 5. Again, for a capacitance C to earth and conductance capital G per unit length, we have the equation minus del I equals to G E into del x plus C into del E del T del x. Again, we are dividing this equation by delta x and take the limit as delta x tends to 0. We obtain the differential equation which is written in equation number 6. The equation is del I del x plus G E plus C del E del T equals to 0. Now, if we eliminate I from equation 5 and equation 6, we obtain a second order partial differential equation in E, which is written in equation number 7. Del 2E del x square equals to L C del 2E del t square plus R C plus L G into del E del t plus R G E. Similarly, if we eliminate E from equation 5 and equation 6, we obtain a second order partial differential equation in I, which is written in equation number 8. So, if we observe equation 7 and equation 8, both E and I satisfy a particular equation, and that equation is known as telegraphy equation. From the telegraphy equation, if you assume that resistance R equals to 0 and capital G equals to 0, then the above equation, or if we observe equation 8, we can see that the equation reduces to del 2 phi del t square equals to small c square del 2 phi del x square, and this is nothing but one dimensional wave equation, where the constant small c square is defined as 1 by L C. So, from the telegraphy equation we can get wave equation. Therefore, it is possible to get wave equation or a hyperbolic differential equation in electrical problem. Now, we are going to discuss about the sound waves problem. Suppose plane waves of sound propagate in a horn with cross section given by Ax with abscissa x such that each point of that section has the same longitudinal displacement xi xt. Then xi will satisfy the differential equation del del x of 1 by A del del x A xi is equal to 1 by c square del 2 xi del t square, where c square equals to dp d rho at 0. The suffix 0 here denote the value of dp d rho in equilibrium state. Now, if you assume that the cross section A is uniform, then A can be taken as a constant. Therefore, the above equation reduces to the form del 2 xi del t square equals to c square del 2 xi del x square. This is again a wave equation in one dimension. Now, in this problem, the change in pressure can be written by the formula P minus P0, where P0 is the value of the pressure in equilibrium state, is equal to minus C square rho 0 del xi del x, where rho 0 is the density of the gas in the equilibrium state. If, for instance, the sound wave passes along a tube which is free at each of the ends x equals to 0 and x equals to a, then the solution of the equation 10 is nothing but the wave equation, is to be determined subject to the condition del xi del x equals to 0 at x equals to 0 and x equals to a. So, these are the boundary conditions for this particular problem. Now, we are going to discuss about sound waves in space. Suppose the sound wave in a gas has the velocity v, which has components u, v, w at a point x, y, z, and p, rho are the pressure density respectively. Then if P0, rho 0 are the values of pressure and density in equilibrium state, then we can write rho as rho 0 into 1 plus s and P as P equals to P0 plus C square rho 0 s, where S is the condensation of the gas and C square equals to dP d rho at equilibrium state. Now, we have the equation of motion rho dV dt equals to minus grad P, where capital D dt is the total derivative, which is equivalent to del del t time derivative plus derivatives in space, which is u del del x plus v del del y plus w del del z. And if you assume that the oscillation is very small, that means for this case we can discard or neglect the nonlinear terms. Now, if we substitute this here, that means we are substituting the value of P and V and neglecting the nonlinear terms, we get the equation which is written in equation number 11. Rho 0 del V del t equals to minus C square rho 0 grad S. Now, if we think about the continuity equation, the continuity equation is given by d dt of rho plus rho divergence of V equals to 0. So, in terms of small s and V and neglecting the nonlinear terms, the continuity equation reduces to the form which is written in equation number 12. Rho 0 del s del t plus rho 0 divergence of V equals to 0. Now, for irrotational motion of the gas, there exists a scalar function phi such that the velocity v can be written as gradient of the scalar function phi. So, v is equal to minus grad of phi, and if we substitute this value of v in equation 11, which is shown here, it reduces to the form gradient of del phi del t minus C square S is equal to 0. while substituting this V is equal to minus grad phi in equation 12, it reduces to the form del S del T equals to grad square phi, which is written in equation number 14. Now, eliminating S between the equations 13 and 14, we obtain the wave equation, which is written in equation 15, del 2 phi del T square equals to C square grad square phi. Thus, for sound waves in space, we again get the wave equation, three-dimensional wave equation. Now, we are going to discuss how wave equation can come for an elastic wave in solids. Let small v, which has components u, v, w, be the vector at a point x, y, z of an isotropic elastic solid. Then the stress components are given by, these are the normal stresses, tau xx, tau yy, tau zz. The expression for these are written, you can see in the slide, and the tangential stress components, which are tau yz, tau zx, tau xy. These are given by the equation which are written here. So, the expression for the tangential stresses are mu into del w del y plus del v del z, del u del z plus del w del x, and del v del x plus del u del y. Now, in this equation, in equation 16, we can see two constants lambda and mu. They are known as Lamé constants. Now, in absence of body force, the equation of motion can be written in the form del del x of tau xx plus del del y of tau xy plus del del z of tau zx equals to rho into del 2u del t square. If the displacement vector v is expressed in the form v is equal to gradient of phi plus curl of psi. So, displacement is divided into two parts, one is the gradient part and another one is the curl part. So, if we substitute 18, in 16 we get the equation del 2 phi del t square equals to C1 square grad square phi and del 2 psi del t square equals to C2 square psi, where the constants C1 and C2 are given by C1 square equals to lambda plus 2 mu by rho and C2 square equals to mu by rho. These C1 and C2 are known as longitudinal and transverse wave speed respectively. So, if we look at equation number 19, then we get that both phi and psi satisfy the wave equation. Now, I shall discuss how wave equation can arise in electromagnetic problem. Now, let us express the magnetic field capital H and the electric field E in the form H as curl of some vector capital A and E equals to minus 1 by C del del T of capital A minus grad of phi. Now, the Maxwell equations are given by these four equations which are written here, where rho is the charge, I is the current and C is the velocity of light. Now, if we substitute the expression which is written in the first line for H and E, then we obtain the equation for the vector capital A and the scalar capital phi, as you can see in the slide. Grad square A equals to 1 by c square del 2A del t square minus 4 pi by c I, and the equation for phi is grad square phi equals to 1 by c square del 2 phi del t square minus 4 pi rho. Now, in absence of charges, that means in the first equation if I equals to 0, the equation reduces to del 2A del t square equals to c square grad square A, and in the second equation if rho equals to 0, then the equation for phi becomes del 2 phi del t square equals to c square grad square phi. Thus, we get that both the vector quantity capital A and the scalar quantity phi satisfy the wave equation which is written in equation number 20. Thus, in module 1 of chapter 6, we have discussed about the occurrence of wave equation in many physical problems, namely in vibration of a string, vibration of a bar, sound waves in space, electromagnetic waves, etc. Therefore, it is important to study wave equation from physical point of view. In this way, we end this module.